Today we embark on a breathtaking exploration of tilings within the vast expanse of the two-dimensional plane. In older videos, we spent some time studying periodic tilings generated by reflection groups, as for instance this plane-filling honeycomb. But this time our attention turns to the famous Penrose tiling. The intricate arrangement of rhombic shapes is celebrated not only for its aesthetic appeal, but also for its aperiodic nature, which intertwines with fundamental concepts in mathematics and physics. In this presentation, we concentrate on one particular aspect of such Penrose tilings, namely that it can be viewed as a projection of a five-dimensional cubic lattice onto a particular two-dimensional plane. I first witnessed such a construction on a Mathematica notebook crafted by Dugan Hammock. The projection of such a Penrose tiling involves a lot of elegant mathematics. There are eigenvectors of five-dimensional rotations computed, projections performed, and a convex hall constructed. All these elements conspire magically to eventually create the celebrated Penrose tiling. And this presentation will walk you through all the necessary details needed to understand its incredible emergence. Once you completed this video, you should in principle be able to perform such a construction by yourself. Before we lay out the details of this construction, it is instructive to investigate the basic algorithm in 2- and 3-dimensional toy examples. In 2 dimensions, a cubic lattice is just a square grid. The lattice points are located at integer coordinates. There are not enough dimensions left to project this lattice onto a plane. Therefore, we show the projection onto a line. The shape of the projected lattice depends on the slope of this line. For most of the slopes, however, the projected lattice will be a mess. Even for our finite part of the full grid, the line is completely filled with lattice points. Only for special angles like 45 degrees, gaps between the vertices appear. There is a neat procedure to pick exactly one layer of lattice points, roughly aligned with the projection line. Consider the unit square. It is defined by 4 corners and represents our cube in 2 dimensions. From the 4 corners we can compute a largest and smallest distance from the line of projection. These 2 values define a zone. All lattice points within this zone are selected for projection. We highlight these selected vertices in yellow, and you can nicely observe how the selection varies with the slope of the line. Eventually, we also show the edges that connect the selected vertices. There's always exactly one connected line of edges between all the vertices inside the zone. Beside the slope of the line, there are 2 more degrees of freedom. We can shift the unit square that defines the zone. This shift only mildly affects the shape of the selection. A second variation is introduced when we shift the entire lattice. Finally, the selected vertices and their edges are projected onto the red line, and we end up with a one-dimensional tiling. Generically, there are 2 different kinds of tiles. One kind originates from the horizontal grid lines, and the second one is the projection of the vertical lines. We color code this difference in green and orange. It is also kind of obvious that there is a periodic pattern of short and long tiles when the slope of the line is rational, and an aperiodic pattern otherwise. Let us summarize the 4 main steps that will generalize to 5 dimensions and present the corresponding linear algebra that we used to generate these animations. First, we need to construct the lattice points at integer coordinates. Additionally, we can offset the entire grid by some shift, which only makes sense to vary between 0 and 1 in either direction. Within this lattice, a line of projection is placed, which will turn into a plane in higher dimensions to obtain 2-dimensional tilings. The orientation of the line is completely determined by its normal, and its components are expressible in terms of the angle of the slope phi. From the corners of the unit square, we can define the maximum and the minimum distance from the line of projection. Later, the unit square will be replaced by the unit cube, or its 5-dimensional brother, a so-called hypercube. From the smallest and largest distance, we construct a zone of selection. Only lattice points and edges inside this zone will contribute to the projection. Last but not least, the projection is performed. For every position vector, the orthogonal component is computed and subtracted. This way, only the parallel part of the lattice survives and shows the tiling that appears on the line of projection. Let us repeat these 5 steps in a 3-dimensional cubic lattice. Here, each integer-valued lattice side is occupied by a vertex. All these little cubies are actually just corners of unit cubes. As you can see, it quickly gets crowded. Therefore, we only consider vertices that are close to our plane of projection. Again, we make use of the unit cube highlighted in light blue to define 2 planes that limit the zone from which we select vertices. In the edge on view, it almost looks like the 2-dimensional case, but this time we have more degrees of freedom for our rotations. Next, we include the faces of the cubic lattice that lie completely inside the zone defined by the blue unit cube. The pattern of these faces depends on the orientation of the zone with respect to the lattice. In the final step, we add a plane of projection and project the selected vertices and faces. The shape and size of the projected faces depends on the angle of rotation. Now we have seen the strategy for the second time that we are going to apply to a 5-dimensional cubic lattice to obtain the Penrose tiling. Amazingly, our brain can easily reconstruct the 3-dimensional cubes from the projection. However, I'm afraid that most of us won't be able to reconstruct the 5-dimensional cubic lattice from the 2-dimensional projection. But just in case there are some of you who can do it, let's have a look at what you should look for. How do 5-dimensional cubes look like? Before a cube is generalized to higher dimensions, it is a useful exercise to generalize it to lower dimensions first. At first sight, it might seem a bit arbitrary to identify a point, a line segment, and a square as corresponding cubes of lower dimensions. But there is a generic procedure to inductively construct cubes of arbitrary dimensions. It consists of 2 steps. First, add a new dimension to your scene. Second, drag and trace the existing cube by 1 unit into the new dimension. We apply this principle 3 times to a single point and inevitably end up with our familiar cube in 3 dimensions. First, a new dimension is added. Next, the 0-dimensional cube is dragged by 1 unit into the new dimension. On the way, it traces out an edge. We obtain a 1-dimensional cube that is made of 2 vertices and 1 edge, also known as unit line segment. When we repeat this construction for a second time, a new dimension is added and our 1-dimensional cube is dragged by 1 unit into the new dimension. It traces out a unit square. The 2-dimensional cube now contains 4 vertices, 4 edges, and 1 face. It will be no surprise what happens at the 3rd iteration. When a new dimension is added and the 2-dimensional cube is dragged into the new dimension, the familiar 3-dimensional cube materializes with 8 vertices, 12 edges, 6 faces, and 1 enclosed volume. Although this cube is presented to you on a 2-dimensional screen, your brain converts this sequence of images into a 3-dimensional solid. Unfortunately, this won't happen when we repeat this construction again. No matter how skillfully we choose the way to project a 4-dimensional cube, our brain will not be able to convert it into a 4-dimensional cube. Most likely this is due to the shortage of experience. But although most of us cannot comprehend higher dimensional cubes visually, it is nevertheless possible to understand their properties. The collected data can help us to spot patterns that we can generalize to higher dimensions. For instance, the number of corners seems to double each time. This is obvious from the construction principle. However, it is instructive to understand the sequence from another point of view. When the coordinates of the corners are written down in various dimensions, one can realize that all possible tuples of zeros and ones are occupied by the vertices of the cube. With each new dimension, each existing tuple can be extended by either 0 or 1. Therefore, the number of tuples doubles for each new dimension, and we will have 16 and 32 vertices in 4 and 5 dimensions. Similarly easy, there is always one component of highest dimension. a face in 2 dimensions, a volume in 3 dimensions, and similarly in higher dimensions there will be one 4 volume and one 5 volume. The number of edges can be computed from combinatorial considerations. In 1 dimension, a vertex can connect to exactly one edge. In 2 dimensions, each single vertex can connect to 2 edges. This generalizes so that in n dimensions, one single vertex can be connected to n other vertices by edges. But each edge consists of 2 vertices. Therefore, there are n over 2 times as many edges as vertices. In 4 dimensions, there are 32, and in 5 dimensions, we find 80 edges. Similar thoughts can be applied to the number of faces. In 2 dimensions, there is one face attached to every edge. In 3 dimensions, each edge is boundary of 2 faces, in 4 dimensions 3, and so on. Therefore, the number of faces can be calculated from the number of edges multiplied by the number of dimension reduced by 1. Additionally, since each face is surrounded by 4 edges, this fourfold overcounting has to be taken into account. We are close to our limits of visualization. It is possible to show that in 3 dimensions each face is attached to one volume. But it's not hard to imagine that with one additional dimension, each face could be attached to 2 volumes and so on. Therefore, the number of volumes is related to the number of faces multiplied by n minus 2. And since each 3 volume is surrounded by 6 faces, the factor of 1/6 takes into account the corresponding overcounting. Finally, the formula for the computation of the 4 volumes follows in similar spirit. As an additional check of consistency, one can calculate the alternating sum of all numbers in one row. In each case, we find the result 1. People familiar with topology can recover the Euler characteristic. But the most important takeaway for all of us should be the increasing complexity. In 5 dimensions, there will be 5 edges and 10 faces that meet at each corner of the cube. With these numbers in the back of our mind, we can start searching for the Penrose tiling inside the 5-dimensional geometry. Obviously, we expect that a Penrose tiling only emerges for very special planes of projection. Fortunately, we can get some inspiration from our 3-dimensional toy model. The most appealing tiling from the 3-dimensional cubic lattice arises when the plane of projection cuts diagonally through the lattice. Then also its normal pokes diagonally through the cubes and points the same amount in all directions. A priori, it is not at all obvious how this setup can be generalized to 5 dimensions. Just remember, in 5 dimensions, each plane has 3 orthogonal directions. It turns out that a successful road to generalization is paved by a rotation that defines this plane of projection. This particular rotation interchanges all 3 axes of the coordinate system. In the animation, you can witness the cyclical permutation of the axes. The x-axis is turned into y, y is turned into z, and z is rotated into the x-axis. This rotation leaves the normal of the plane invariant. Let us have a closer look at this rotation. It can be described by an orthogonal matrix. The eigenvalues of this matrix give further insight. The eigenvalue 1 corresponds to the normal vector, which we identified as eigenvector before. The other 2 eigenvalues are complex conjugates of one another and encode the rotation. The corresponding eigenvectors are complex. However, their real and imaginary parts define an orthonormal basis for the plane of projection. Do you get a feeling for what comes next? This normal vector and this particular rotation can easily be generalized to 5 dimensions. And indeed, this will lead to a plane of projection suitable for a Penrose tiling. Now the rotation cyclically permutes 5 directions. One eigenvalue is 1 and corresponds to the normal poking diagonally through the lattice. But there are 4 more eigenvalues forming 2 complex pairs. Each pair defines a plane. We can choose either one as our plane of projection. The leftover plane will be orthogonal, and together with the diagonal vector it will form the 3-dimensional orthogonal space. Although it seems scary at first to talk about 5 dimensions and 5-dimensional cubes, The problem at hand makes it rather easy to cope with. We always have a two-dimensional plane of projection, which is easy to imagine and to visualize. At the same time, we have three orthogonal dimensions to the plane of projection, which by themselves are also easy to visualize. Only the combination of the two would make things difficult, but we can always consider them independently. This means that every five-dimensional vector can be decomposed into a two-dimensional part on the projection plane and a three-dimensional part in the orthogonal space. If there's just one orthogonal dimension, it's rather easy to decide which vertices to select and which ones to neglect. Things get slightly more complicated when there is more than one orthogonal dimension. In the five-dimensional setup, we have to deal with three dimensions beside the plane of projection. Let us first look at one intermediate step when there are two orthogonal dimensions. To make things easy to digest, we go back to the model where there's just a line of projection. Then we can host it together with the two orthogonal directions inside our familiar three-dimensional space. We now look at the projection of the unit cube onto the orthogonal plane. When everything is aligned nicely, the projection is just a square, and we simply select all the points inside the zone traced out by this projected square. When the line is tilted with respect to the unit cube and the lattice, the projection is more complicated. However, we only care about the outer rim of the projection. This is technically referred to as convex hull. Again, we trace this shape along the line of projection and select all the vertices inside this zone. Alternatively, we can say that we select all grid points that are projected inside the convex hull. Equipped with this intuition, we can return into our five-dimensional world. There are three orthogonal directions to the plane of projection. The corresponding basis vectors are collected in a projection matrix. This matrix is applied to the 32 corners of the five-dimensional hypercube. This generates a point cloud with 32 points in the orthogonal space. The convex hull of this point cloud forms a three-dimensional polyhedron. Its interior will be our filter function. Whenever the projection of a lattice point lies inside this polyhedron, the lattice point will contribute to the tiling, and all faces that are fully contained inside the polyhedron will be displayed on the projection plane. Of course, this particular shape of the convex hull is special for the chosen plane of projection. In the following animation, we will approach this plane orientation step by a sequence of primitive rotations around the coordinate planes. Watch out how this polyhedron appears eventually in the orthogonal space and the Penrose tiling emerges on the plane of projection. Did you really understand what was going on? If not, that's totally okay. We will look at this one more time, but before, let us put ourselves into the perspective of flatlanders. These are poor creatures that only can perceive two-dimensional geometry. What would be their best option to analyze such a three-dimensional cubic lattice? Well, first of all, they can introduce a plane of projection and a line that runs through the orthogonal space. If all points of the lattice were projected onto the plane, this would result in an incredible mess. Therefore, the flatlanders think about a unit cube and its projection onto the orthogonal line. They will only consider lattice sites whose projections are inside the projection of the cube. They will highlight these selections in yellow. In a next step, the flatlanders also want to display all faces whose projections are fully inside the projected cube. This way, they obtain exactly one layer of square tiling. With this basic setup, the flatlanders know that they can perform three rotations of the plane inside the three-dimensional space. The first rotation just turns the plane of projection inside itself. From the flatlander's point of view, we keep the plane fixed and rotate the lattice instead. Since the selected vertices and faces do not change, the tiling only gets rotated. The second rotation turns a coordinate plane that is orthogonal to the projection plane. Now some selected faces move out of the zone and they are replaced by other faces, whose projection now completely falls into the projected cube. When the projection plane slices diagonally through the three-dimensional lattice, the flatlanders will observe such a nice rhombic tiling. The three colors correspond to the three different possible coordinate planes in 3 dimensions. If you feel sorry for the flatlanders' poor perception, well, don't feel sorry for too long, because in what comes next, we will be such poor flatlanders, only able to perceive 3 dimensions, although we would like to understand 5-dimensional geometry. We basically repeat the flatlanders analysis. We introduce a plane of projection and a cell of the 5-dimensional unit cube projected into the 3-dimensional orthogonal space. Now there will be 10 possible planes of rotation, and there will be 10 different colors that highlight the 10 different orientations for the faces of the 5-dimensional lattice. The first projection looks very familiar. Since the plane of projection is aligned with the cubic lattice, we just get the square tiling. The first rotation again only rotates the orientation of the squares. You can see that all selected lattice points are projected into a single point in the 3-dimensional orthogonal space. After 2 rotations, we obtain a tiling that could easily be generated from the 3-dimensional cubic lattice, and our brain can restore the corresponding 3-dimensional structure. Now the projection of all selected vertices lies on a line in the orthogonal space. However, one further rotation tilts the plane into the 4th dimension, and any hope for ordinary humans is lost to retrace the higher dimensional structure from the projection. For a particular orientation of the projection plane, we will eventually arrive at the famous Penrose tiling. If you followed the decomposition of the 5-dimensional rotation matrix carefully, you will remember that we made a choice when we selected the eigenvectors for the projection plane. With a different set of eigenvectors, we would have ended up with a different plane of rotation. This final animation shows the transition from one Penrose plane to the other. All these animations have been created with Blender. We extensively made use of geometry nodes. There will be a follow-up video where these Blender files are explained and made available for your own investigations and real-time animations of the Penrose tiling. You can dynamically rotate the plane in whatever direction you like. You can investigate shifts of the unit cube or shifts of the entire lattice. If you are interested in particular details, let me know in the comments or simply stay tuned for more. That's all for today. Bye bye.